Hi and welcome! Today we're going to take a look at this very late 486 motherboard, the SOYO SY4SAW2. I bought this board from an e-waste recycler on eBay who was selling it for scrap. There were no close-up photos of the board, so I didn't know the exact condition, but it was offered at a reasonable price, so I took my chances. As expected, this is a socket-free board, and it has 4 PCI slots, 4 ISA slots, and even a VESA local bus. It is based on the SIS85C496 chip, which is great as it also includes a built-in IDE controller. And would you look at this! Next to the keyboard connector, there is a header for a PS2 mouse, but there is also solder pads for a proper PS2 connector. Awesome! As you can see, there is leaky battery damage, but it doesn't look too bad. The PS2 mouse header has some green crust on it, but overall the damage appears to be fairly minor. The middle of the board has suffered some mechanical damage. There are some bent pins which look like they used to form a 3-pin header. And there are a couple of SMD components that have been sheared off. My guess is that this was caused while trying to remove the motherboard from these annoying plastic clips with some pliers or something. This tantalum capacitor has some minor surface damage, but looks alright otherwise. We will fix this later, but let's first start with the battery damage. I'm using white vinegar to neutralize the electrolyte. I applied quite a lot of it and let it sit for a couple of hours. Desoldering leaky batteries can be challenging, so let's just cut the battery pins. Now let's remove the green crust. I am scraping it off using a flathead screwdriver. I'm trying to expose the bare copper so that I can apply solder on it. And yeah, this definitely needs some repair as the middle trace has rusted away completely. Before going ahead with the repair, I washed the board with soap and water to remove the vinegar. Now that the board is clean, let's apply some solder to help protect the traces. For the damaged trace, I'm using a small piece of wire to help bridge the gap. Using some flux helps apply the solder. Using a solder wick helps remove the excess solder and get a nicer looking finish. At the bottom of the board there is some minor corrosion too. Let's scrape it off with the help of the screwdriver. Flux helps a lot with thinning these small traces, so I applied quite a lot of it. Okay, now let's check for continuity to make sure that none of them is broken. Finally, let's remove the battery terminals that we cut earlier. Luckily, the solder is not corroded on this side of the board, so I managed to desolder them fairly easily. Let's straighten this header. The keyboard connector has part of the keyboard jack still plugged in. I wonder how this happened. Anyway, let's remove it. Well, the connector is quite bent. And two of its pins that are also connected to ground have broken off. This is not super important, so I will revisit it later, after fixing some more important issues. Okay, let's try to fix the missing components. First, I'm removing the excess solder to make it easier to solder the new component. The solder mask is C37, which suggests that this is a capacitor. I am not sure what value I should use, so I'm just gonna guess, and I'm gonna use a 1 microfarad. The other broken component is marked as R50, which is a resistor. Part of it is still there, so we can see that the last digit is 0. In such cases, checking the redware web can be very useful. I was lucky and I found a great high-resolution photo of this board, so I could clearly see that this is a 100 or 10 ohm resistor. Now let's replace the header pins with a new 3-pin header. Okay, now that we have repaired the most important parts, let's try to power the system on. But before doing so, let's check for shorts at the power rails. Okay, no shorts. Great. Before plugging in the CPU, we should check the voltage at the socket to make sure that the regulation circuit still works. I'm checking pin C4. And yes, it is at 3.39 volts, which looks fine. So now let's plug in this Intel DX4 100. The manual of this board is also available on the RetroWeb, so I'm making sure the jumpers are set correctly. And let's power it on. Great, we're getting postcodes. Let's add some RAM and this S3 video card. And yeah, the system is booting. As expected, we're getting a CMOS error, so let's fix the CMOS battery before moving on. What's really great about this board is that it even has provision for a CR2032 battery holder. But we can't just plug it in without disabling the charging circuit, because the CR2032 lithium battery is not rechargeable. The charging circuit is very simple. It is basically a diode with a 2.2K resistor in series connected to the 5V rail. So all we need to do is remove the resistor and the battery will no longer be charged. By the way, the idea for this mod came from Atheatos' excellent video about this board. He has done a couple of very detailed videos about this specific motherboard, including a video about several cool hardware mods and an overclocking and underclocking guide. Okay, let's remove the resistor and install the CR2032 battery holder. Now let's revisit the keyboard connector. At first I tried applying a lot of solder in an attempt to solder the broken parts together. But this didn't work, as the pins did not get soldered properly. So I removed the solder blobs and the remaining parts of the broken pins. I replaced the pins with this square bracket shaped piece of wire. This can now be soldered across the bottom shielding and make a very solid connection. But I could not get it to sit exactly as I wanted, so I ended up removing it completely. Under the keyboard connector there was some more battery leak damage, nothing too bad, but it had to be fixed. Now let's also remove the mouse header so that we can replace it with a proper PS2 mouse connector. Now let's get back to the keyboard connector. With the connector off the board, I can now attach the wire exactly the way I want. So now let's solder both connectors. I think they look pretty good. Following Atheatos' advice, I added some thermal paste between the voltage regulator and the heatsink. Now let's plug everything in and boot the system. Oh, and let's not forget that for the PS2 mouse to work, we need to connect jumper JP4. Okay, the system boots until the system configuration table, but then it hangs. Could this be a corrupted BIOS issue? I found a later BIOS on the RetroWeb, one that's also modded to support large disks, so let's flash it. And as expected, nothing changed. Well, this is a typical failure when the L2 cache is not working. The cursor blinks at that specific point, but the system hangs. There are two ways to confirm that the L2 cache is indeed the issue. First, we can disable the L2 cache in the BIOS and try to boot. And as you can see, it boots just fine. The second way is to use a post analyzer to check the last post code printed before the computer freezes. And in this case, it is 61. and if we check the post codes for our word BIOS, it is indeed the phase where the system tries to turn on the level 2 cache. Okay, now that we know the problem, how can we fix it? Well, there are a couple of things we can do. First, we can try swapping the cache chips with some other ones that we know they actually work. This is the first thing I tried and didn't fix the issue. So we know that this is not an issue with the cache chips, but there is something wrong with the board. The second thing to try is to check for broken traces. This is fairly common for motherboards that have suffered mechanical damage, like mine, which came from e-waste. It is also common with boards that have leaky batteries. The spilled electrolyte can sometimes find its way and damage traces that are quite far from the battery. My motherboard had both issues, so this was the next thing to check. Checking for broken traces is fairly simple. You just need to check that all the pins of the cache chips are connected to the places where they are supposed to. The I/O pins, shown in blue, are usually connected directly to the chipset. The address pins, shown in red, are common across all cache chips, and even the tag chip, though not in the same order, and they should also connect to the chipset. In this board, the chip enable pins are controlled through a 7408 AND gate IC. The output enable and write enable pins are shared across the cache chips and are also controlled by the chipset. Well, I checked all of these connections with a multimeter and I found no open circuits. So logically, the only thing that looks suspicious is the 7408 that controls the chip enable pin. Let's remove the chip and test it with the EEPROM programmer. The test passed, but let's install a socket and try another chip just in case. As expected, that didn't fix the issue either, so I put the original chip back. Okay, now that we know that no traces are broken and that the 7408 is not the issue, let's check the signals on the oscilloscope to get some hints. All address and I/O pins should show some normal activity. All address pins do, except this one at A10, pin 23, which is always at 0. But what's even more strange is this output enabled signal at pin 24. This is active low, but as you can see it is showing some strange noisy signal. This signal comes directly from the chipset's K-Rex pin. So perhaps the chipset is damaged and produces this bad signal? But this is hard to believe as everything else seems to work. This was a very strange issue. At that point I had run out of ideas, so I stopped working on the board for a couple of days. A few days later I wanted to revisit this board. I went through the datasheet for this chipset trying to look for clues, and while I was browsing the text, I saw these cache-related timing diagrams that show that the chip's A clock was very important for getting the timings right. The documentation says that A clock is the advanced clock, which is the same as the CPU clock, but 3 to 5 nanoseconds earlier. I traced the A clock on the board, and what a surprise! It is connected to the capacitor that I had replaced with a random value. What a coincidence! As far as I can tell, this capacitor is part of an RC circuit on the PLL's output, and it seems that both the A clock and the CPU clock have a similar RC circuit. My guess is that the RC circuit is meant to provide this 3 to 5 nanosecond delay that the manual was talking about. Okay, let's check with the oscilloscope whether we can actually see any delay between the two clocks. The waveform is not great, but I don't think I can tell any time delay, so the A clock is definitely wrong. But what capacitor value should we use instead? Let's take a look at the circuit. In both cases the resistor is 10 ohms. The CPU clock's capacitor is 680 picofarads, so for the A clock signal to come earlier, we'll have to use a smaller value. The RC time constant for a 10 ohm resistor and a 680 picofarad capacitor is 6.8 nanoseconds. So to get a 5 nanosecond difference, we would need an RC time constant of 1.8 nanoseconds, so a 180 picofarad capacitor. The closest value I have is 100 picofarads, so that's what I'm going to use. Let's replace the 1 microfarad capacitor with the new 100 picofarad. And let's try to boot. And success! The L2 cache gets enabled and the system does not hang. And let's take a look at the signals. Well, the peak of the yellow signal, the A clock, looks a bit earlier than the green one, but I'm not exactly sure. And how about the output enable signal? Well, it doesn't look that much different, so perhaps the chipset was not working correctly internally because of the bad A clock? Anyway, it seems to be working better than before, now with the new 100 picofarad capacitor, but I'm still not confident that this is the correct value. If any of you has the same board and can measure this capacitor, I would greatly appreciate it if you could let me know about the correct value of capacitor C37. Okay, that's all for today. I hope you enjoyed the video, and as always, thank you for watching and goodbye.